It's a real pleasure to be back here to a place which basically I call home, because it's you know, where I've spent many years of my life here. It's what I'm going to talk to you about today is this question that I've got on the screen, right? Should we observe spirals in young planet-forming disks? These young disks are what we call self-gravitating disks. Here on the screen, you can see an artist's impression of one of these disks. It's an artist that you'll recognize. This is actually a simulation of mine, which I gave to Amanda, and she produced this absolutely wonderful image of it. So I thought it was very appropriate to actually start by showing you that image. So you see, these disks have these really, really beautiful spiral structures, and that's the topic that I'm going to sort of focus on today. So self-gravitating disks, these are sort of the natural outcome of the star formation process, right? What you're seeing with this movie here, this is a simulation of a molecular cloud. It's rotating, it's collapsing, and in this whole process, you get stars forming. You'll see these little dots on the screen where you have stars forming, and around those stars, made out of the same material, that molecular cloud material, you will get disks forming as well. Here's one example in the bottom right, just there, where you've got a disk forming around. I think that might be a binary star, in fact. You can see that this cluster environment is really dynamic. There's a lot going on here. And in this initial phase, because these stars and disks are surrounded by the envelope is naturally, it's feeding the disk. The disks are most massive during this phase. Now, when they're massive, they actually show these kind of spiral structures. This is one of my simulation images of a self-gravitating disk, where really you see the self-gravity is really driving the evolution of the disk and actually forming these spiral structures. Now, we're at a stage where we're starting with ALMA to be able to really observe disks and really try to understand the structure of these disks and the causes of the structure that you have in these disks. Here are a couple of examples which actually are thought to be self-gravitating disks. We've got strong evidence that these are actually self-gravitating disks. On the left-hand side, you have the Elias 27 disk, and if you look sort of in the top right of this image here, just there, and then also in the bottom left here, you see these two sort of large-scale spiral structures. This is roughly about a 300 astronomical unit disk. And it is, and that was something that was really very exciting when it first came out, because we thought maybe this is a good example of a self-gravitating disk. It, in fact, was the first example of a self-gravitating disk. So it was really exciting for those of us in the community who've been working on these disks for so long, but hadn't actually had the observational confirmation of these. On the right-hand side, you have the AB Auriga disk, and that's something that's come out just recently this year. We've known about these spirals, but really the work has been done to really kind of give this strong indication that these spiral structures are due to the self-gravity. Now, when the disks, we expect that the disks will be self-gravitating when they are young, because they are most massive when they're young, because of the material that's sort of coming from the molecular cloud and feeding onto the disk. What's really interesting about another couple of really young disks is that these do not show spiral structures, right? So both of these are much less than about 500,000 years old. We might expect these to show spiral structures if they were self-gravitating, but instead we see sort of a ring structure, we see gaps. On the right-hand side, you can see this a little bit more clearly. The R's mark the rings, the G marks the gaps. Where are the spiral structures in this? In these young disks, and that is the really intriguing side of things. You know, why are we not seeing spirals in these? So that brings me back to this question that I put on the screen to start off with: should we actually observe spirals in these young disks, right? Given that all disks should pass through this self-gravitating stage during their evolution, should we actually observe these? And a different way of actually trying to answer this is, or ask this, is actually, well, why haven't we observed many spirals in young planet-forming disks? Right, so I've been working on self-gravitating disks for, well, nearly 2 decades now, since I was a master's student doing my Part 3 project. And back then, we had only been in a position where we had actually started observing protoplanetary disks about 10 years before that. So we were really thinking more about the theory side of things. It was a dream to be able to actually be in a position where we might be able to observe these disks. And so, you know, people like myself and others in the community have worked really hard to try and kind of progress the theory of self-gravitating disks. So this is the background from which I come from. I run numerical simulations to understand the evolution of self-gravitating disks. But now what I think is really key, and what's interesting about the times that we live in now, is that we can do this with a view to really try and understand the observations, or perhaps the lack of observations, of spirally disks. So I mentioned that the self-gravitating phase lasts for a very, very short period of time. Here's just my sort of rough sketch of a protoplanetary disk's timeline. Disks are typically expected to last for somewhere between 3 and 10 million years. And the self-gravitating phase of that actually lasts for much less than half a million years, right? In fact, that red box should probably be a little bit narrow, but if I made it any smaller, you probably wouldn't see it. What I want to get across with this is that it might be that it's difficult to observe these disks simply because the chances of actually observing disks that are in that short initial phase is somewhat low. That certainly could be a possibility. The other aspect is that, well, we have to also consider that because these disks might be in the cloud environment, it's much harder to see them because we've got to look through the molecular cloud in order to be able to actually see those disks. But if I just remind you, we have seen young disks, and we have seen disks without young disks without the spiral structures. So then we've sort of in recent years we've been starting to think more about what properties, what processes can go on in disks that might actually erase the spiral structure. So here are 3 aspects of my talk that I'm going to focus on. I'm going to start by talking to you about planets in self-gravitating disks. Now, around sort of 2011, we started trying to think about the fact that, well, what would actually happen if we had a planet in these disks, right? Now, these self-gravitating disks, these are some of our numerical simulations. You've got this very sort of spirally turbulent structure, and what we did was to just simply put a planet in this disk in order to try and just see what happens in terms of the migration of the planet. Now, what we found, if we look at the right-hand side, what you're seeing here is a plot of the separation, so that distance between the planet and the central star, against time. And what we did, because these disks are so turbulent, there's a lot of stochasticity involved here, we repeated these simulations 8 times, right? So we started off with a planet sort of up here at 100 AU, and then we also put a planet at sort of various different azimuths in 8 separate simulations, and that's what you see on the right-hand side. Ultimately, you see that there's some stochasticity. The planets will sort of be kicked outwards, they'll move inwards, but generally they migrate inwards very, very rapidly. That's the sort of take-home message with this work. But what I want to point out is that we actually modeled these disks using very, very simple thermodynamics. In reality, the disks are not entirely turbulent from the inside all the way to the outside, and we'll look at that in just a moment. But if it's only turbulent, what the stochastic kicks that you get that kind of causes the planets to move very, very rapidly, this actually really is really important to consider, and therefore it's really important to think about where we see that turbulence due to the self-gravity in the disk and the impact that it has on the planet. Now, some other authors, Dimitri Stamatelos and collaborators, actually looked at this in a little bit more detail. And what they actually did was to actually simply model these disks, but taking into account the thermodynamics far more realistically than we had done in our initial paper. What you're seeing here on the y-axis, again, this is separation against time. It's the same kind of plot that we were seeing on the in the previous slide, but what you see this time is that these planets sort of start to migrate inwards, but they do actually end up stalling, right? These are various different simulations that they were running, and the details of that are sort of not so relevant here, but what I wanted to point out is that when you do start to think about the thermodynamics in more detail, actually it does change the migration pattern of the disks. Now, there's two aspects to think about with regards to the work that they did. The first is, as I mentioned, they modeled the thermodynamics more realistically. They were doing this with a radiative transfer code, and that was something that can definitely play a part. The other aspect is that they allowed the planet mass to grow. That can also play a part in the migration pattern of these planets. Now, what we wanted to do was to sort of separate these two and just try to figure out what it was. Was it the thermodynamics, or was it the actual planet mass? And so here are two images from two simulations. One which I call an unrealistic self-gravitating disk, which is basically one which is turbulent from the inside all the way to the outside. It's a bit like the simulation image that I showed you 2 slides ago, where you had a lot of spiral structure. On the other hand, what we have on the right-hand side is what I call a more realistic simulation, right? We have turbulence in the outer part of the disk, which is what we expect for self-gravitating disks, but in the inner part, it's a lot more smooth, a lot more quiescent. And so what will happen with regards to the planets interacting with the disk will be very different to what you have in a disk which is entirely turbulent. Now, before I show you the results of this, I want to introduce a parameter. This is the tumor stability parameter. This gives us an idea of how stable a disk actually is, right? Now, in a self-gravitating disk, you've got a number of forces that are at play here. You've got the pressure forces and the rotational forces in the disk, which act to stabilize the disk. And opposing that, you've got the gravity forces. And this is what you see in this equation here. So this is the tumor stability parameter, that's Q. You've got your pressure forces, which are represented by the sound speed here. Kappa is the epicyclic frequency, which is roughly of the order of the angular frequency. That's your rotational side of things included there. And then your gravity forces are here in the sigma. Pi and G are just constants, of course. And so it's really those stabilizing forces versus the destabilizing forces that we're thinking about here. Now, what we know from work that's been done many, many decades ago is that these spiral structures will develop in these disks if this tumor stability parameter is less than about 1.7. Let's actually look at the simulations that we've done, right? On the top panel, what you have is a simulation without a planet. In the bottom panel, you've got a simulation with a planet. We've actually started the simulation. We've sort of evolved these disks to start off with without a planet. And what you're seeing right now is that the two are at exactly the same time. hopefully that will, what you will see is that the top one continues to evolve, and you can still see the spiral structures at the end of it. And what you see in the bottom panel is that the planet, this 3 Jupiter mass planet that we've put in there, has interacted with the disk, and it's completely got rid of those spiral structures. So we can try to understand what exactly caused the spiral structures to disappear. Well, let's start by looking at this tumor stability parameter here. So just a reminder, this is the equation here, and there's 2 key factors to think about. There's a sound speed, and then there's a surface mass density. Now, these plots are quite busy, so I'm going to walk you through them. Let's start with the top plot here. This is the tumor stability parameter. And the reddy pinky lines are the ones from this no planet simulation. The blue lines are from the simulation with a planet. And what you're also seeing on these plots is a time evolution of these parameters, right? So as the color gets darker, so as you go into darker and darker blue, you're going later and later in the simulation. And similarly with the red, the darker the red, the later you are in the simulation. What you see from that top panel is that things don't change with that red line at all. Generally, that tumor stability parameter just stays pretty constant throughout the simulation. What you see with the blue case is that later in the simulation, so the darker colors, you actually have an increase in this stability parameter. Let's actually try and understand why. In the middle plot, we're seeing the surface mass density, right? And what you can see generally is that in both of these simulations, things don't change with the surface mass density too much, right? But what is changing is the sound speed, right? In the case of the red lines, of course, there's nothing changing in that simulation, so the temperature doesn't change at all. But in the case where you do have the planet, that's actually causing the disk to actually heat up. So you see that the darker blue are sort of higher up here, and that's what's contributing towards a higher value of Q and just simply the disk becoming more stable. Now, this is actually happening because of that interaction, that shock heating that occurs due to the interaction between the planet and the disk. Now I asked the question about whether or not these we should be observing spirals. We can actually look at we can actually look at sort of the mock observations of these simulations. So firstly, we've got the situation without a planet. On the left-hand side, there are spirals here just in the purple. It's very hard to see. But what we did was to actually, in the middle panel, we have an axisymmetric model. We subtract one from the other, and you can see the spirals in the residuals on the right-hand side. We can also do this for the case with the planet. And when you take the axisymmetric models away from sort of the mock observation of this case with the planet, you don't see the spiral structures like you do in the top panel on the right-hand side. You see a little bit of the interaction between the planet and the disk, but those grand design spiral structures are not there. So the important thing to take away from here is that the disk mass didn't change. All that changed was the temperature, and that was enough to sort of drive that disk out of the self-gravitating sort of phase and into a phase where it was sort of much more stable. The second topic that I want to cover is the idea of warps in self-gravitating disks. So warps might be present in these disks for a couple of reasons, right? I showed you that initial simulation of the molecular cloud collapsing, and you see that there's a lot of stars. This looks a little bit grainy here, sorry about that, but each of these are sort of stars. You can see that we're in a sort of a clustered environment. There's a lot of interactions between the stars and the disks. It is highly likely that you would get some kind of interactions which can lead to a disk not being coplanar but actually being misaligned. You might also get misaligned infall into the disk as well, right? We're in this envelope embedded in this molecular cloud. It's not necessarily the case that you would have an even amount of material flowing onto the disk. What's more likely is that it will actually be asymmetrical, and so this can also lead to some kind of misalignment in the disk. So what we did was to actually try and simulate a self-gravitating disk. We said, right, okay, what happens if we have a warp in a self-gravitating disk? And this was a really, really nice kind of first step to try and understand what happens in these disks if you've got warps. So what you're going to see are two movies. The simulation is identical. On the right hand side you're going to see the side view, the edge-on view, so that you can see what's happening to the warp. On the left hand side we're just showing you it slightly sort of face on, so that you can see what happens to the spiral structure. So as we evolve these disks, see, we start off with the spiral structure at the very beginning. Over time you see that that spiral structure actually disappears. The warp also disappears, and that's absolutely okay, because in this numerical experiment we didn't sustain the warp, we just left it to do its thing and just to see what actually happens. But what you see here is that you've completely lost the spiral structure, and that you've ended up with sort of this sort of more axisymmetric structure. So we see that the warp actually gets rid of these spiral structures, and let's actually look at the tumor stability parameter and just see what actually happens in terms of the stability side of things. So again, here is our tumor stability equation here. We're interested in the sound speed and the surface mass density, because those are the two aspects that are critical in determining the tumor stability parameter. In each of these, the color bars show the time evolution. So again, the darker the color, the later we are in the simulation. And if you see this first plot here of surface mass density, what you see is that all the lines pretty much lie on top of each other, meaning that things don't change with the surface mass density. But things do change when you look at the middle panel and you look at the sound speed, right? As you evolve, the dotted line is the initial case. As you evolve these simulations, you see that it gets hotter and hotter over time, and that temperature increase is what leads to an increase in your stability parameter, right? Recall that if we increase our Q, our spiral structures could disappear, right? We only have spiral structures if the tumor stability parameter is roughly less than about 1.7. So again, it's not the disk mass that's changing, it's the temperature that's changing here. And the reason why the temperature is changing here is because we have this radial pressure gradient that is taking place here, right? That misalignment between the inner and the outer disk actually induces this really strong radial pressure gradient in the direction that you see these arrows pointing in. And then this affects the gas radial velocity, which then ends up heating up the disk. What you see on the bottom panel, if we look at the left-hand side here, this div V is basically a proxy for the PDV heating in the disk. And what you see is that in the direction of the warp, you have this sort of strong heating that's taking place here. And that's actually what actually leads to that's actually what leads to that tumor stability parameter sort of heating up. Just to very quickly explain this equation on the right hand side, that radial pressure gradient is roughly, this is the pressure, this is the scale height in the disk, this psi is the warp amplitude. So the stronger the warp amplitude, the more the radial pressure gradient and the more the heating you would get in the disk. And then what you see afterwards, just by comparison, once we've lost the warp in the disk, you see that heating has just sort of completely gone. So it really was the impact of the warp that was playing a part here. Just as a quick side note, we did also see a bit of a ring and a gap structure in these disks. It's interesting because we actually see a lot of disks with rings and gaps. I showed a couple of those young disks at the very beginning. We don't know whether this is numerical or whether this is physical. We're still sort of trying to work through that. So it's interesting, but we still need to kind of try to think about that in more detail. So the third topic that I wanted to mention is this idea of fragmentation in self-gravitating disks and the impact that can have on the structure of self-gravitating disks. Now, self-gravitating disks can evolve, and if the conditions are right in the disk, these disks can actually fragment in the outer parts to form companions. In our case, this may be sort of brown dwarf, they may be planetary mass companions, they may be brown dwarfs, they may even be stellar mass objects as well. What you see in this movie is that the outer part has actually kind of fragmented into little sort of gas balls that will then ultimately evolve into these various different objects. Now, it's really interesting to look at the fragmentation side of things and the impact that might actually have on a disk. Here is one observation of a disk that may that is thought to have fragmented into a protostar. You've got a star in the middle, another star here, and here further out, this is a part of the disk where these authors actually looked at this and said this is actually a part of the disk that they think is actually unstable, where that Q parameter is quite low. So this is actually quite massive. It's 89 Jupiter masses. But what's interesting is that it's in the part of the disk that is thought to be unstable. So there's certainly potential observational evidence for this. And so we can start to think a little bit more about sort of the parameter space for fragmentation and also for spirals. What you're seeing with this plot here, this is a really nice plot that Tom Howarth came up with. And what he did was to do a suite of simulations looking at different stellar masses and different disk to star mass ratios. And what he was really interested in exploring was to actually look at the impact that the passive heating from the central star, what impact that had on the disk, right? So what he was actually seeing here was quite interesting, right? At very low disk to star mass ratios, so low disk masses, what we were seeing is that we don't actually see a lot of spiral structure, right? We see generally it's quite axisymmetric. At slightly higher masses, we see that you do get some spiral structure. But if we look at any one of these columns, let's look at 0.7, for example, right? At low disk masses, we don't have spiral structures. We can increase those, and then we might be able to see those spiral structures. But if we continue to increase, that disk is so massive that it can actually fragment and break apart. And again, here we've sort of lost that spiral structure, right? So there's sort of this lower, the smaller sort of parameter space, if you like, in between where you might actually see spiral structures. Now, thinking about whether spiral structures actually exist or not, we can also just think a little bit more about how well we're actually modeling these disks in terms of their thermodynamics. Here is a really nice example from Alison Young, where you can see that in one implementation of the thermodynamics, which is what you see on the left-hand side, you see these spiral structures. What happens on the right-hand side is something different, right? So this is meant to be more realistic, yet the spiral structures are much less pronounced. And you've certainly got experts here as well. Kat's done a lot of really great work thinking about sort of the irradiation from the central star and the impact that it actually has on the disk in terms of its structure, but then also the fragmentation side of things as well. So when we're thinking about modeling these disks more realistically, we actually end up losing those that very pronounced spiral structure. When we've kind of gone one step further and we've gone, well, actually, maybe we should really kind of model these disks really properly with radiative transfer. And this is what Saul Rauther actually did recently. He did a comparison between two simulations. On the left-hand side, what you'll see is sort of this live radiative transfer where we're attempting to model the disk with radiative transfer that is, really with a lot of detail. And what he's done is to compare it to the right-hand side. This is what we call beta cooling. This is a cooling method that has been used a lot in the past, myself included. And one of the advantages that beta cooling has is that it's computationally inexpensive. So we can use it to really try to understand what goes on in disks, but certainly it's not sort of, the realistic way of modeling disks, but it's very, very useful to be able to see what goes on. What happens when we simulate the left-hand side is that these simulations take a very, very, very long time, and so that's why people have sort of tried to sort of stay clear of it unless they've got really good computational resources. Now, let me actually play those two simulations, those two movies. What you see is that over time, that beta cooling, you'll see these spiral structures develop. You've already seen them develop in the live radiative transfer case. But what happens in the live radiative transfer case is that you actually, that heating, that irradiation from the central star is what determines the temperature structure in the disk. On the right-hand side, the cooling ends up determining the temperature structure in the disk. Whereas in the left-hand side, with that irradiation from the central star, because it's sort of the temperature structure is now controlled by what's going on from the irradiation of the central star, any PDV work or shock heating is sort of negligible there. And that's not the case on the right-hand side. So what's happening in the left-hand side is that it's really the surface density evolution of the disk that's actually driving what's going on, right? There's a lot of angular momentum transport happening in the spiral arms, and that actually ends up reducing the density in the outer disk and actually stabilizing that disk. So again, when we move towards trying to model these disks more realistically, again, we're losing those spiral structures. Now, if you might think, well, okay, let's just bump up the disk mass, because if we bump up the disk mass, we should, that self-gravity should be stronger and we should see those spirals. But as I showed you with Tom Howarth's work, you bump up the disk mass and you actually end up in a stage where you do actually see fragmentation. And yes, you can still sort of see some of the spirals here, but as these sort of evolve, you do actually lose those spiral structures. So that brings me to the end of my talk. I'll just quickly summarize what I've talked to you about. Essentially, I'm thinking about whether or not spiral structures should be there in young discs and whether or not we should actually observe them. And I talked to you about 3 ways in which we might actually wipe out the spiral structure. The first way is where we have giant planets that interact with the disk and completely wipe out the structure. The second way was where we have warps, and the warps actually cause heating in the disk, which can then again wipe out the spiral structure. In fact, in the first way also we're seeing heating in this case as well, due to that planet interacting with the disk. And then in the third way, we see that you might be able to see the spiral structure as you increase the disk mass, but really there comes a point when you actually fragment the disk, so there's only sort of this small parameter space where you might actually see spiral structures. So very quickly to point out that especially with the first 2 and a little bit with the third one, the disk masses don't change too much, right? Now, that's really important, because when our observational colleagues go out and actually look at disks, if they say, well, this disk doesn't have spiral structures, so it can't be very massive, that may not necessarily be the case. It might be that there's something else going on in the disk that is causing those spiral structures to be wiped out. So with that, thank you very much for your attention, and I'll be very happy to take any questions.